Mi amor. Bueno, ya. No. No. Systems, this condition is guaranteed because the identity matrix is present in the sampling process when you discretize a system approximately or exactly. So that's a technical condition that is very helpful in some of the things that we will be doing next. In particular, for instance, for linear system in which that condition is automatically present because of the Cayley-Hamilton theorem, you have a very simple condition. The image of this vector map B gets in complement with the range of A to obtain the full state space. That means that if you provide U with all possible control inputs in the real line, and the image of A is mapped in this manner linearly, then you obtain a non-empty, a non-empty open set in Rn. That's important for invertibility. If you have, let's say, a hyperplane or something like that, you wouldn't guarantee the existence of that inverse, and reachability would be compromised. So in that perspective, we can talk about controllability in general terms, and we would define a system to be controllable in the usual sense if you're given an initial state and a final state, which are located in a sufficiently large open set of Rn, then you would be able to find a sequence of control inputs, in this case, real values because the inputs are scalar, which when applied to the system initialized at x0, at most n steps, you will get to the final value xf. And because of the time invariance, it doesn't really matter where you start or where you initialize your system. The important thing here would be the existence of that sequence of control inputs that would take you at most in n steps to the final desired value. So for that reason, we can dispense temporarily about the time labeling of the elements in the sequence of inputs, because that turns out to be unimportant. What is important is the structural properties, and controllability is the first important structural property of dynamical systems which are being controlled. So we will take a generic control input in the open set U, and from that we will propagate our system. For instance, it's important to emphasize that if you don't apply any control input at all for a long period of time, your state will evolve naturally according to the dynamics of the system in a drift manner, in the sense that from that initial state, you will reach some states after n steps, and those states are only a function, of course, of the initial state, because you are not applying any particular input. This kind of influence on the response of the system will always be present, and in the linear case corresponds to the natural evolution of the system. When the control is 0, you have an exponential matrix multiplying the initial state. Well, in here, when you have this set of states reachable from the initial state with no controls being applied, you have also some subspace, because you will obtain this iteration of the map on the initial value, and therefore you will have some values of the state. Those values of the state will appear again even when we're controlling the system, because we analyze the dependence of the full map with respect to the controls and the states, and at some point this map will appear again in the next few slides. And we can dispense of that value by saying, well, it doesn't really preclude controllability, because if it is present there and my system is controllable, I can always move my state to a place where part of this will be canceled, where this will be canceled, and the other part will be the desired state. or otherwise, I will move my system state to a specific one in which, when composed with this additional state present there, I will obtain the desired one. So in general, those states represent a reachable set of states when no control input is being applied. So that term is harmless and is always present, and in the linear theory, it has a very clear interpretation. Here we will see that we have something similar. So let's examine the evolution of the state, the natural evolution of the state. And for that, this delta operator is just the next state. So delta x is just xk plus 1. That's the system model. We have a nonlinear next state map, which depends on x and depends on u. In this context, is very illuminating to obtain the differential of that advance of the state. By the differential, we just mean the partial derivative of the map with respect to x multiplied by the differential of x, and the partial derivative of the same map with respect to u multiplied by the u. This is an important operation because it brings to light the dependence of the next state in terms of the, let's say, actual state and or something which is in the state space, and the dependence on the control input. This and has the advantage of being a sum of two differentials, so we're actually in a linear space. It will turn out that this combination is, which is, by the way, the combination of a matrix times a vector, which is a vector, and this is a vector by itself. The derivative with respect to scalar continues to be a vector times a scalar that gives you a vector. So we're adding things here in a vector space, if you want. And that vector space might be defined on the field of the real numbers, for instance, no problem. But it's much more convenient to define that vector space on a different field, and that field is the field of what's so-called meromorphic functions. Those meromorphic functions are just quotients of analytic functions. You see, analytic functions form an interesting ring of functions, because when you multiply two functions, they are not generically zero, because analytic functions, you know, they cannot be zero on open sets. If they are zero on open sets, they are zero everywhere. So these linear combinations, sometimes we like to think of this linear combination as obtained through the use of quotients of analytic functions, which gives you more generality, and those functions are functions of the state. So we don't have to restrict to the map itself as it's done in linear systems, but we can expand a little bit our view by saying this is so generic that even if you multiply this vector by a function, by a scalar function of the state, and you multiply this matrix by scalar functions of the state, you don't destroy the rank of this sum of vectors. That's the technical reason behind sometimes invoking meromorphic functions. It's just to say that we have a much more general linear combination of things, not constrained to the real numbers, but we can throw in the coefficients of the linear combination, we can throw in analytic functions or quotients of analytic functions, which are called meromorphic functions. So like if I had polynomials in the state, now I would be able to put as factors, as scalar factors of those vectors, rational functions of the state. So that gives enough generality, and it doesn't cost anything to expand that from the field of reals to a larger field of functions, because they will usually appear everywhere in the treatment of nonlinear systems, whether they are continuous or discrete. So the next state after xk plus 1 would be xk plus 2. and that would be obtained by delta square of x. That's the symbolism for xk plus 2. And that's a composition of nonlinear maps. The nonlinear map depending on the control, and the state is updated to a new state through the same nonlinear map. So we have this composition, we symbolically put it as phi square, although it's not entirely rigorous. We would like to say that we're iterating on phi with all its arguments, with all its arguments in this manner. So that simplifies the notation, but when we have something like this, what we mean is really this, a function of a function. And as we iterate, we have more complex compositions of functions in the manner dictated by the structure of the next state map. So if we take the differential of this second order iteration, we will have, in the first place, we will have the partial derivative of this iterated map with respect to x, and then again with respect to x. That gives us the product of two matrices. These two matrices will appear there because the first one is the partial of the whole map with respect to, pardon? Sorry? Somebody's trying to talk to me, but it comes out very chopped. Okay, so when we take the partial derivative with respect to x, we have to take into account that this internal dependence also is a function of x. So we have two partial derivatives with respect to x, generically speaking, and therefore the product of those two matrices will appear in the dependence of x of this map. And then we have to take partial derivative of respect to x one time, and then with respect to x, with respect to u the second time. And then we have also a single dependence on the first map with respect to u that will give us this term. So this is whatever depends on u is collected here, and whatever is, so to speak, the natural evolution of the system without taking into account the control input is responsible for the presence of this iterated or product of matrices in the iteration of the nonlinear map. So when we have that, we start to build up a structure in the state space through the differentials, which is much more clear than what we have in the nonlinear cold map of composition of nonlinear functions. Here you start having some vector space structure thrown in, and that is very nice just to assess the structural aspects that are going on. If we take the third composition or the third advance of the state, now everything will look very much the same, except that here we will have a third power of that matrix, and here we'll have a composition of this vector map, and then the product of this matrix times this vector, and then we'll have this move to the right, multiplying this square of this matrix times the same vector partial phi with respect to u. And that is very reminiscent of the way that in linear systems, the reachability subspaces start growing as you apply more and more input, or as you move from one instant to the next. What you're getting is somehow the Kalman song, in which you have, remember that in linear systems, this corresponds to B, this corresponds to AB, and this would correspond to A square, but in the next time slot, you will have this matrix multiplying B. So you'll have B, AB, A square B in the linear case. So we can continue with that evolution through the composition of nonlinear maps and just picturing what's going on in the space of these so-called one forms, in which you just take the differential of the next value of the state and relate it to whatever is being generated by state themselves and what is being generated with the help of the control. And what you end up is precisely with this sum generalized to n terms, in which you have the same structure of the power of certain matrix multiplied by B, and you add all those contributions over the time span identified with the initial state, with the initial time to the nth step. So in doing that, whatever is relevant to controllability being produced by either the open loop action of the control or the closed loop action of the control is summarized in this term, because this term has the same nature of the previous one that we examined when we were applying no control. Probably the control input will be here, but it will not be part of the map that one gets with this. And whatever the presence of the control there, it doesn't bother you. And this summarizes the explicit dependence of the control in the whole evolution of the system. So whatever is reachable has to be a composition in the differential space, or in the space of one forms associated to the system, will be present in this sum. And the image of this vector and these maps is what gives you the reachability space in this linearized, it's in fact a sort of a local linearization in which you respect two dimensions, the contributions of the inputs and the contributions of the state, tangled in such a manner that they are acting recursively on each other and expanding the dimensions or not, in order to assess the possibilities of reaching any particular state in the state space. And when this map conforms to the totality of the state space, then we will say that the system is controllable. And by that, we mean that just the span over that set of meromorphic functions, which is the most general span that we can think of, because it even contains the span of the reals, and a little bit more than that, the span over all the set of meromorphic functions. This matrix, this vector, has an image, and that image is being mapped and added by powers of this matrix. So locally, the controllability of the whole system would imply that you can go in any direction in that sort of tangent space, tangent with respect to u and x, that locally at least points towards new directions as the dimensions increase and times is going on, and the time clock is ticking. So, so in the state space, the controllability condition would be to have this rank of this sum of contributions in that linear one-form space. It's a vector space anyway. Is just the reproduction of the Kalman controllability matrix in a more general setting. So the rank over all those meromorphic functions of the so-called Kalman controllability matrix has to be n. And here the crucial role is being played by the submersive system assumption, because this matrix, whenever it's not full rank, this vector is not collapsing. So in a way, that assumption guarantees finiteness of this argument all the way up to obtain controllability. And in fact, when you have a linear system, this is just precisely that. The linear system would replace the nonlinear map in this manner, and pardon? Phi of x and phi of u would be A and B, and what you have in the previous slide is just the controllability matrix, and the rank condition is the rank of the controllability matrix being n. So we have the reproduction of the well-known Kalman matrix rank condition for the particular case of linear systems. And And of course, controllability is invariant. We know that controllability is invariant with respect to partial feedback. We talk about partial feedback when we replace the input coordinates by a state-dependent transformation that involves a new auxiliary control input. So a change of input coordinates has to be interpreted as partial feedback. I feedback the whole state by means of a control law that has the provision of letting free the possibilities of using an auxiliary control input to complement whatever need might come ahead. So partial state feedback is defined in this manner, and it can also be equivalently interpreted as an input and state-dependent input coordinate transformation. And the assumption here is that this map or this transformation is invertible. Remember that U is a scalar and V is also a scalar. So the condition for local invertibility of this input coordinate transformation, which depends on the state, is that this partial derivative of the map phi with respect to the control input V is non-zero. So that allows us to define well an input coordinate transformation which depends on the state, because we can go back and forth from original input variables to auxiliary new input variables. So the composition of the original state map with the feedback control law partially controlling the system and letting the option free to continue controlling it through a different control input modifies the system dynamics to a new form, but it's in essence is just the same discrete time system evolving now in terms of a new control input through a modified next state map. And when you do that, it's easy to see that the evolution of the transformed system through time gives you modified maps of the same nature as before, but in the space of one forms, it's the space of functionals on the state. It's a dual space basically. You recover the same structure for the state because you're not doing anything to the state, and in the linear dependence with the actions of the control input, you get this non-zero factor multiplying the previously obtained vector, and therefore the image of this vector is not going to be modified because this quantity has been specifically assumed to be different from zero. So the whole influence of this modification only refers to this growing sum of terms, which is related to the Kalman controllability matrix, and pretty much the state map gets no modification which is visible in terms of the state. So the contribution is that everything you had before is pretty much the same, except that each term in this sum is being multiplied by a non-zero factor. Since this will be a meromorphic function in general, then that doesn't affect the rank of this matrix, and therefore the controllability is not affected by the input coordinate transformation. And the same happens when you do a state coordinate transformation. Controllability is a well-known fact, does not get modified by state coordinate transformations. And here we think of invertible state coordinate transformations. This is the relation between the new state, which is a vector, and the previous and the actual state X through this map, and this map is a column vector. So this transformation is assumed to be invertible in the sense that I can solve uniquely for X in terms of Z. So our nonlinear discrete time system gets modified by this change of coordinates. And when you do that, you obtain the new system in this manner. The next transform state is just the nonlinear map being used as a transformation, acting on the entirety of the state map. And the state map itself is modified in the dependence of the state because the state is being transformed. So in essence, what you have is a composition of your invertible transformation with the next state map, and internally you have the presence of the inverse of the transformation, replacing X by the function, a function in Z. So the modification is just that, but the structure is here in this tangent space. And this is why, I'm sorry, the modification is here in the composition of maps. And in the tangent space, we can see what that does now to the part that explicitly depends on the state, which is now changed to the vector Z, and how that evolves in this dual space of one forms is just to take, you know, the differential of these composite functions, and the differential of this composite function is the partial differential of the transformation, and then followed by the product of the partial differential of the state map, and then by the partial differential with respect to its argument of the inverse of the transformation. So this matrix comes out naturally in this space of differentials, portraying the influence that the state itself has in the evolution of the new system, and how this affects the influence of the control is through a non-singular matrix partial of phi with respect to X transpose. Recall that if this vector function is full rank, that means that all the gradients of phi are independent, and therefore this matrix is non-singular. In essence, then, we're meddling a lot with the state, but we're just influencing the image of this control input channel in a manner that is non-singularly portrayed by the gradient of the transformation, and that is a full rank matrix. So when we keep doing these iterations of the states through the state map in the transform system, they have a very interesting sort of chain of compositions of functions in which you have clearly some simplifications, because, for instance, when you compose the transform next state map by means of that state coordinate transformation, then when you replace the expression of that transform map but by what it actually represents in terms of composition with the transformation, you will have this composition that you can, by simple observation, you will see that you will have the transformation of the entire system, and internally you will have the transformation of the entire map, and then finally the transformation of the dependence on the state. And when you do this composition and examine the differential, everything becomes product of matrices, and you see that there is some natural simplifications. This inverse map will be canceled with this direct map. And so phi will be composed with phi, because these two transformations have the virtue of annihilating each other. So phi square will appear, and that will bring us to the gradient of this transformation times the gradient of phi with respect to X repeated 2 times, and then finally you have this. So very nicely, the things that you know in linear systems start also being generalized here in terms of complex expressions, in terms of partial differentials and so on. But what is important is that the part that has to do with the willful presence of the control input modifying the evolution of the system is in these red terms. And those are being modified only by an invertible matrix. Therefore, the rank of the red portions is not changed, because this preserves the rank, given that it itself is a full rank matrix. Therefore, controllability, which is which is circumscribed to the presence of this term, is not affected by the state coordinate transformation because the influence on the image of the whole reachable subspace in that vector space is just a full rank matrix, and therefore the rank is not lost. There is no collapse of dimensions there. Therefore, we have the result. And similarly, we can examine another very important structural property, which is observability. And that property just establishes the possibility of finding the state which initiates the system of evolution solely from the basis of the applied string of inputs and the measured outputs, which are sort of the way that the external world communicates with the system and the way that the system communicates with the external world. And whatever internal things are going on in the system are summarized in the state, and therefore we can examine the possibilities of recovering the states from the measurement of inputs and outputs. In fact, it turns out that since the inputs are known, it's more interesting to circumscribe the property of observability to a system which evolves with no inputs being taken into account, or in the concept that we establish, we just take a next state map autonomously evolving thanks to the initial state and measurements being made by means of a scalar function h called the output. If you agree to that the influence of the control could be computed and could be subtracted from our system of equations that will give us the initial state in terms of the measured outputs, then the key question of the property is related to this system rather than the control system. But the control doesn't bother you because you know the control input and you measure the control output. What you are after here is your initial state. And generically, you can assume that that state has any value x. Therefore, the important thing is here how the output evolves as time goes on and the clock is ticking. The composition of h with the nonlinear output map is giving you the value of the evolution of the output at each moment, and you compose now properly the composition of phi, which itself will be called properly phi squared as before. And since there is no control input, this string of equalities is clear when you analyze the natural evolution of the output in terms of a nonlinear map, which implies the compositions of the output map with the next state map in a recursive manner. So the evolution of the output, which is supposed to be known, will allow you to compute uniquely the initial state x if this vector map, which we call O of x in reminiscence of the observability property, if this map, which is an n vector map, is invertible in the sense that you can obtain x uniquely from knowledge of the advances of the output, then you will have an observable system. And for that, this map has to be invertible. And invertibility of this map is just the independence of the row vectors of the gradient of these compositions. So in the dual space that we're beginning to use, the gradient of all these scalar entries have to be independent, but not only independent in terms of the field of real numbers, but they might be independent in the field of meromorphic functions, and more generalities gained by assuming that. So this map has to be invertible, and therefore I would be able to compute x, which is the initial state in terms of the advances of the output, uniquely when that map is invertible. Of course, we don't expect this to be invertible globally, but probably locally. And we have agreed that we're looking at a sufficiently large open set of state space where all these things, all these operations will have some meaning and will produce some results. And therefore, the condition is simply that the rank of those gradients, which now imply compositions of H with the matrix partial of phi with respect to X transpose, those compositions turn out to be this product of row vectors times matrices, and the result is that each row vector appears in this matrix. And if the rank of this is full, that means that the original map is invertible. And therefore, if this rank is generically n, then we will have observability, and we will be able to uniquely solve, at least in a local manner, for the initial state given the sequence of advances of the output. So this is observability, and in particular, let me call you to the attention that formally, at least, this expression gives you the gradient of H times this matrix. The gradient of H times this matrix will be the gradient of H times each one of the columns in this matrix. But that column, each one of those columns is the partial derivative of phi with respect to some state X sub I. So what we have is a collection of directional derivatives of H in the directions of the columns of this matrix. And we're stacking all those scalar directional derivatives in a single row vector. So we can analyze, we can summarize this also as a generalization of some directional derivative in which we have the, let's say, formally the lead derivative with respect to all these columns of the scalar function H. So this expression would be synthesized in this very simple notation as the gradient of H multiplied by each column vector of the matrix 5 sub X, which is the gradient of phi with respect to X. So if the rank of this matrix is n, what we're saying here, at least formally, in reminiscence of what's done in continuous nonlinear systems, is that the set of directional derivatives are all functionally independent, or they produce a matrix which is full rank. And the rank doesn't have to be measured in terms of real numbers, but can be established in terms of meromorphic functions, which gives you much more generality. Therefore, observability just reduces to finding the rank of this matrix, or if you prefer in terms of actual coordinates, the rank of all these row vectors produced by products of row vectors times matrices. And for the linear case in which the system is quite simple, the advance of the state is just generated by an action of a matrix on the state, and the output map is a linear function of the state, then phi is just that, and the output map is this set of linear operations. So the gradient of phi is just A, and the gradient of H is just the vector C transpose. And the previous observability matrix just conforms to the Kalman observability matrix, and the rank condition can be taken in terms of real numbers because there is no functions here underlying the presence of all these basic maps that constitute the linear system. So this rederives the Kalman observability condition. And of course, observability is invariant with respect to invertible state coordinate transformations. The fact that you change your state variables from a new viewpoint doesn't destroy the possibilities of computing the initial state from the evolution of the state itself. So when you do that composition, through this invertible state coordinate transformation, you have the same property that we saw before. Here, this is the transformed output map related to the state, and this is the next state transformed output map in which you have the composition of H with the state coordinate transformation composed with the state coordinate transformation and the next state map and the inverse of the transformation signal in the presence of C rather than X. Therefore, here you have simplifications because these compositions are directly one on top of each other, and therefore they simplify naturally, and you sort of reproduce the observability matrix, but in terms of the new state. So nothing really changes, given that the state coordinate transformation is invertible. This just produces the same action of the observability matrix on a different value of the corresponding state, but it doesn't change the essence of the observability. Therefore, as you can see here, what happens is that the observability matrix is being multiplied by a non-singular map, non-singular matrix, which is the gradient of the inverse transformation with respect to the new variable C. Therefore, the composition of those maps on the transform system just entitled the use of a non-singular matrix multiplying all these gradient vectors on the right. And therefore, the rank doesn't change because this matrix is full rank itself. And that gives you a very well-known result that observability is not affected by state coordinate transformation. And with those two things, we were in position of examining what is the relative degree, because the relative degree will be a concept linking inputs and outputs, sort of jumping through a springboard of the state. Therefore, input to state, which is controllability, and state to output, which is observability, will be engaged alternatively in the direct relation from inputs to outputs. So we will be able to use the notation that we were using in the observability and controllability concepts in the relative degree, in the establishment of the relative degree. The relative degree, we define it as the natural structure that links inputs to outputs, of course, passing through the state and sort of neglecting the state in between. But of course, we will see that everything can be discovered by a state coordinate transformation. And so what we do is that we define a process in which we repeatedly forward the time shift of the output function, generating functions of the state and the control input. And possibly we assume that in those iterations, you will not find the presence of the input immediately, but that you will find it sometime along the process of iterating the next state map in the relation with the output. You will find the explicit presence of the input after some, let's say, R steps forward are being taken. So what we're assuming is that the evolution of the output from the initial value of the output to the value of the output associated with the first forward time shift and the second and the third and so on, up to some R-1 step, the presence of the input is not there in those compositions. That means that the evolution of the output does not have an explicit presence of the control input up to some iteration of order R-1. But that the next one, the next iteration, is already a function of U by the first time. Of course, there is a silence possible presence of U everywhere, but it is not explicitly. And this is the remark that I would like to make in order to define the relative degree. Of course, the input is immediately affecting the state, and the state is being affected, and the state effects on the state are being sense it at the output. But the issue is, when I do the computations of composing the output map with the next state, do I find the input explicitly in that expression? And that might not be true, that you find the output there. So we're assuming in general terms that it takes some time, some iterations to find the presence of the control input explicitly in the output evolution. And once it is found, that presence, we stop at that moment and say the system has a relative degree given by the number of steps that took us to reach that explicit dependence. So the relative degree will be defined to be R if this is the case. If these two set of equations, the red ones simply saying there is no explicit influence of the input in those evolutions of the output, and there is a presence of the input in that particular time point in which you reach by means of your iterations. Therefore, this is our definition of the relative degree. And as usual, what we can do is to relate those iterations by means of map compositions. And so the first advance of the output, which is H composed with phi, the output map times the next state, that doesn't depend on phi. Well, that means that this partial derivative should be zero. But according to the chain rule, this partial derivative is the product of two partial derivatives. One of them, the partial of H, which is only a function of the state, as initially assumed, will have to be derived with respect to X. And then the chain rule says you have to derive the internal dependence of the function phi with respect to the control input U. And this is zero. So this product of partial derivatives are zero. This is a row vector, this is a column vector. So what we are going to do is to assume that this is a directional derivative, a formal directional derivative of H with respect to this vector phi U. In the sense of differential geometry, that wouldn't be quite the case, but formally in the calculus of Rn, you can, say that yes, this is the gradient being projected on the dependence of the next output map in terms of U. This is sort of the input channel processing the gradient of the output, the natural way in which the output is going to grow with respect to the state. And that is zero. That means there will be some sort of orthogonality there. So we say that this is the directional derivative of H with respect to the vector phi of U. Phi of U is the partial derivative of phi with respect to U. And this is zero, because this is the first evolution of the output. It's not supposed to have any explicit dependence on U. So it's important to remember that H composed with phi is not a function of U. It's only a function of the state. And that is why this partial derivative becomes zero. And in the composition of the next output, the composition of H with phi 2 times, which essentially what we're doing is something like this, we can proceed as before, just remembering that this partial derivative is zero. So, and therefore this is only a function of the state. So when we have the second value of the output in the time of evolution, we would have this partial derivative with respect to U. And that, according to our assumption, should also be zero. So let's compute that specifically. The composition of H with phi is a function of only the state. Therefore, the chain rule says you have to derive this with respect to X first, and then you derive the next composed function with respect to U, and that will give you this dependence. Because remember, this does not depend on U, according to our previous assumption. Therefore, we have this product. And this partial derivative is just the partial of H with respect to X transpose. and multiply by the partial of phi with respect to x. And then therefore we have this triple product of this row matrix, row vector, full n times n matrix times column vector. This triple product is therefore scalar, and it should be zero if the second forward shift of the output is not to depend on the control input. And therefore you continue iterating, and you will start obtaining these products of this row vector times some power of the matrix times the column vector depending on the input. And when you do that, you get to the final conclusion that the rth minus 1 iterated value of the output through the state will not depend on the input either, and we will have simply this formula in which we generalize this to certain power. This power is always one integral value less than the number of iterations. So here we have 2 iterations of the state map. You have only one, the presence of the first power of phi. You have r minus 1 iterations of the state map. You will have r minus 2 in the power of this matrix. Therefore, this is 0 because we haven't reached our initial assumption in which only the rth iteration will of the state map will depend explicitly on the input when you see it from the output. And therefore, that last term is different from 0 in general, and this would stop the process of finding the relative degree. The relative degree will be R, means that this triple product, which is a scalar quantity, is going to be different from 0. But the previous ones, all of them here in blue, are yielding a 0 value, indicating that there is no explicit presence of the input in the natural evolution of the outputs through the state map. So the relative degree gives you that integer number, and notationally we are going to use these directional derivatives in a formal way. Remember that the partial of phi with respect to u is a column vector, but the partial of phi with respect to x transpose is an n times n matrix. So substituting these two things in the previous chain of relations, you will have, in essence, directional derivatives, first with respect to the input channel, and then with respect to the product of the state matrix in the dual space, multiplying the input channel a number of times, expressing the powers of that matrix. So in essence, what you have is a nice reminiscence, although it's not exactly the same, reminiscence of what you have in a continuous time case, that all these directional derivatives of H with respect to the input channel vector, the product of the state vector or the state matrix times the input vector powers of up to order r minus 2 times the vector give you all 0. All these directional derivatives in a formal way give you 0. And then because of the presence of the input in the last iteration after this one, you will have the presence of the input, therefore making this scalar quantity non-zero. And that is our definition of the relative degree in specific terms involving the input channel and the state, so-called quote-unquote state matrix. So the first row vectors are going to be these row vectors. They turn out to be linearly independent. And that's a very important property, because it means that the matrix that you're building with these row vectors, one on top of each other, at least up to this point has full rank, has rank R-1. So in a sense, this is giving us the possibilities of building a state transformation. And naturally, these first row vectors, if they are linearly independent, then the corresponding map will have at least that rank. So all we need to do after that is to complement those gradients with new vectors that are linearly independent between them, among them, and linearly independent with respect to these first found vectors. So the fact that they are linearly independent is very easy to show. Let's assume, contrary to what we have established, that this collection of row vectors is linearly dependent, although we put something a little bit stronger than saying this collection of row vectors, when multiplied by meromorphic functions, reproduce zero. That we're contradicting what we're saying, that these are linearly independent. We assume that they are linearly dependent, but not only linearly dependent with respect to combinations, to linear combinations of these row vectors with real numbers, but also with meromorphic functions. It doesn't make any difference, and it gives us more generality. So let's assume, contrary to what we want to show to obtain a contradiction, that this linear combination, there exists some functions, alpha sub j of x, some meromorphic functions, which annihilate the sum of row vectors. And if that is true, then I can solve for the last summand of this sum, the last term in this sum. I can solve for that in terms of the previous ones. And that would be a fact. This last term will be a linear combination of the previous ones, provided, you know, I keep this factor, which is a non-zero factor, and that's what we're assuming. For a linear combination to be proper, all of this cannot be zero. So at least the R minus 2 will not be zero, and we will be able to obtain this relation. If that were zero, then it means that there is a smaller set of row vectors which is also linearly dependent, and we could go on like that for some time. But in essence, without loss of generality, I would assume that this is not zero. So this expression can be written in terms of a linear combination of the previous elements in the sum. And now what I do is I multiply both terms of this by a vector, which is by a vector which is just phi xr times phi u. When I multiply both terms of the sum by that quantity, what I get here is that this term, according to my assumption, this term should not be zero because this is different from zero, and we're assuming that this coefficient here is non-zero. Therefore, this, according to the relative degree definition, this should be different from zero. And on the other hand, in the right-hand side, the multiplication by that factor, which is non-zero, gives you zero in all the elements of this remaining sum. So this has to be zero. If that is true, this cannot be zero. Therefore, you have chosen a zero element for alpha r minus 2. And you repeat the argument solving for alpha r minus 3 times the corresponding nonlinear composition of maps in the tangent space, in the dual space. And then by the same argument, you will reach the conclusion that alpha r minus 3 is also zero. And you keep going and you will conclude that all the alphas have to be zero for that to be true. Therefore, we have a contradiction, and that set of row vectors has to be linearly independent. So the assumption was wrong The assumption that they were linearly dependent is wrong, and therefore these advances of the output as functions of the state are part of a map that has, up to this point, full rank R. And in so doing, our intention is to use all these maps which have independent row gradients as part of a transformation. But so far we only have R of them, and we need at least N to complete the state coordinate transformation. So the gradients of all these maps are linearly independent, not only with respect to the reals in the field of reals, but also with respect to the field of meromorphic functions. And all we have to do is to come up with some independent new functions, let's call them eta of R plus J, from J equals 1 to N minus R. So we'll have N minus R additional functions to complete the transformation that so far is interesting because it has complete rank R. And so we complement the state coordinate transformation by throwing in functions whose gradients are independent between themselves and also independent with respect to the first R gradients of these maps that I computed, spanning the natural evolution of the output until you hit the input. So in fact, there is enough freedom to obtain these complementary functions which might be assumed to be functionally independent. Their gradients will be their gradients will be linearly independent. And moreover, I can even assume that I can have sufficient freedom, and that's part of some examples that we're presenting in the next few slides, that the next output map corresponding to these complementary coordinates is such that they don't depend on you. This is an assumption that is comfortable. It doesn't mean that the states that will be reached by this have to be necessarily independent of the input in the revolution. No, but it's some static assumption that will get rid of the control in this part of the transformation that we're proposing. And the reason will be clear when we obtain the full transformation and obtain the transformed system. So we're assuming that the composition, at least the first composition of these complementary functions completely in the rank of the transformation that so far needs to be complemented all the way up to order N, is such that the next value does not depend on the input, and therefore is only a function of the state. That's not crucial, but that gives you a better definition of the zero dynamics without having to worry about what the control is doing to the first coordinates. And that's the only reason, is for aesthetic reasons rather than practical reasons. And of course, getting rid of the presence of the input here is also convenient from a manipulation viewpoint. So we assume that, and there is always enough freedom to do that, and we will see that through very simple examples. So we complete the transformation of this first R coordinates, which are the compositions of this map, having independent gradients, with some new states which also have independent gradients, some functions of the state, nonlinear functions of the state, which have independent gradients, and which are independent also, those gradients are independent of the gradients of the first R gradients. And that's always possible to do. Here, because I have enough room to propose complementary dimensions to the dimensions spanned by the gradients of these functions, so that I fill up the whole crate up to n independent row vectors. the assumption that the next state is independent in this particular coordinates is independent of the U is a preciosism, is something that is only for static reasons, and it doesn't bring anything new. The important thing is that all these maps will not have the presence of the input explicitly up to this order of the map. And therefore, doing that, the interesting thing here is that if this is the output and this is the next output, if I call this the first state, then the second state is just the first state advanced by 1 unit of time. This is the nice thing about this chain. And H composed with phi will have an X value, which is H composed with phi squared. So naturally, we're inducing here a chain of iterations which have a nice linear time forward shift structure in which the first state, when shifted in time, reproduces the second state shifted in time reproduces the third. And that's a nice song because it gives an essence of linearity, at least to these first R coordinates. And this is what we get. In fact, by adopting those as a state coordinate transformation, all those maps which are well defined because all these gradients are independent and therefore the rank of this matrix is n, given that the rank of this is R, and the rank of these complementary coordinates is such that I have chosen them to be independent with independent gradients and independent of the first ones. There is always room in the n-dimensional space to specify that. What I will have is a very nice linear iterative structure in which the states being produced are the elementary version of the next one shifted 1 unit of time. And therefore, up to the Rth equation, I will not have the presence of the input, but simply this nice linear forward time shift relation reproducing the new states consecutively from the first one, which is just the output, to the first one, which is just the output, towards the one in which the input appears for the first time through these nonlinear compositions of maps, in which here you no longer can be denied because this represents the Rth plus 1 value of the output, starting from the initial value of the state all the way to the presence of the input. So here I have been able to identify by means of that state coordinate transformation that there is a very nice, almost linear structure between the input and the output, except for that this nonlinear function is a function of the output map and the iterated next state map composition. And but essentially, if I am able to call this an input coordinate transformation and substitute that by a new auxiliary input V, there would be no doubt that between this auxiliary control input and the first state, there is a perfect linear relation. And this, the ladder that I established going up will lead me to the output itself. So the relation between the output and the input will become a linear relation modulo a small partial state feedback transformation or input coordinate transformation, which might be well defined because recall this thing in the dependence of U is non-zero. And therefore, locally, I could solve for U if I equate this with an auxiliary control input V. Therefore, in these new coordinates, I have something very, very nice and very comfortable. There is a hidden linear system inside my nonlinear system in which the relation is an elementary forward time shift relation from the output to the input, given the dimension of the relative degree. That's the dimension of the linearization of the input to output map. And that is very helpful, because now the fact that every nonlinear system has a hidden linear system that I can unmask, I can take out the disguise by simply looking at a different state rather than the original one, in which that linear relation becomes evident. Now I will have the possibilities of using linear control tools to design a nice behavior between the input and the output. Modulo the inversion of this nonlinear map, which is assumed to be invertible according to the definition of the relative degree, I would have the possibilities of controlling this through a different transform input with all the tools that I have available from the linear theory. And what about the remaining states, those that I specifically gather as functions that had row gradients that were independent among themselves and also independent of the first gradients of the transformation that I use to uncover this linear relation? Well, those, if the non-dependence of the input in the next value of those states is enforced and is possible, this represents a sort of autonomous evolution of the state, being influenced, of course, by the first R coordinates and itself being driven by the coordinates of these specific variables and the initial values of the state, but with no explicit presence of the input. This is the advantage of having that coordinate transformation being particularized to that which does not contain the specific influence of the input in explicit manner in these coordinates. And therefore, we obtain a sort of a canonical form. In fact, it's called Isidori's canonical form. Every nonlinear system has a hidden partial linear system relating the input and the output modulo an invertible input coordinate transformation. As I repeat, this will allow us to obtain a nice framework for doing control design for stabilization of the output evolution or trajectory tracking on the output reference trajectory tracking in terms of this linearized system. And this linearization does not entitle any approximation. So this is an exact linearization of our nonlinear model. One of the things that will become clear here is that, of course, this dynamics that is present here in the complementary dimensions to this linear space in the state space of the transform variables has an important property. My system is relative degree 1, which is the most elementary relation between the input and the output. I take the next value of the output, and the input is already there explicitly. Okay, that will only circumscribe the linearization to the first equation, and the rest of the equations would be autonomous in this sense, that would depend on the first output, first state, and the rest of all the complementary states. So the dynamics that is not susceptible of using linear tools would be very large. So relative degree 1 means you have a complementary dynamics which is of higher dimension, n-1. And on the other extreme, we would have that if this output is such that the relative degree is n, I mean the whole dimension of the state space is equal to the relative degree of the system, then all the variables in the states would be conforming to a linear input-output relation modulo invertible input coordinate transformation. That means that there wouldn't be any dynamics associated to the complementary dimensions.
Professor.
I wouldn't have to worry about this.
Professor. Yeah, Professor. I have to go to another meeting. Can we have a little bit of break here?
Oh yes, surely. I'm about.
And I want to make one comment. I don't know if it's correct. That this development in discrete time almost exactly parallels what happened in continuous time.
Yeah.
Right.
It's analogous. Yeah.
But you found the discrete time correspondence, and maybe you can provide us with some references, books, and so on, so we can follow up on the study of this. I can distribute your lecture note to the participants, and we can put it in the QQ group. But there's
I'll be happy to do that.
Very intriguing. Yeah. I'm sorry, I have to leave a bit early, but that's very
okay. I understand. I'm about to be finished.
Yeah.
Yeah, I should be finishing. But
I have to go. I have a departmental meeting I have to attend.
I understand. Yeah. Now, since you are the host, you will be able to finish the meeting. I'm willing to.
No, you. I'm the co-host. I think you are the host. I think you are still the host. I'm the co-host, right?
Well, that's what I did. Yeah. But
yeah. Oh, okay. I made you a host. I made so you'll be able to continue to do this. My leaving will not impact it. I have another Zoom meeting for faculty candidate.
Okay, so, good.
Yeah.
Good. Okay. I'll finish at this point, and we'll continue next Thursday. Thank you.
No, you can continue, and people can ask you questions. I think there will be some question coming up.
Okay, but, I'll do it. Okay, thank you.
Bye-bye. Thank you very much for doing this. Thank you very much.
Oh, you're welcome. So, is there any questions? Rafał Modonski raised his hand. Can you talk? Should I habilitate you? No.
No, I'm here.
Okay, great.
Hello, Professor. Hello again. I'm doing very good. Thank you. Thank you for asking. I have a question about slide number 41.
Yeah.
Could you talk about, is there any physical interpretation of those additional functions that we have to design? For example, in case of mechanical systems, is there any guidelines how to choose those functions?
Yeah, in mechanical systems, especially in underactuated systems, those states play the role of what's called the zero dynamic. You see, most popular mechanical systems like robots, they're fully actuated. And if some robot manipulator is not actuated, it's because you want to do a very convincing experiment that you can do useful things with an underactuated manipulator. But some other systems like cars or set of wheels evolving on the plane and things of that sort, there are no linear systems. When you discretize them approximately, because those are non-linear systems, very difficult to discretize them exactly. You have linear systems with multiple inputs. And because there is a degree of underactuation there, you might have zero dynamics. But in essence, what those extra dimensions will bring about is the unobservable part of the system when the output is being controlled towards a specific target like stabilization or trajectory tracking. Those have two properties, those states. If they cannot be controlled because the control is already being used by the first linearized coordinates, and they cannot be observed because when you start controlling the linearized part, you block them from the structure. And therefore they are only influenced by the evolution of the control states. But if that dies out to a stabilization, then you have an autonomous dynamics that has to go towards an equilibrium or drift away from an unstable equilibrium point. So that's a very important part of the dynamics. It's the zero dynamics. We will see the implications of the zero dynamics because they can have a nice, convenient behavior like being asymptotically stable to a unique equilibrium point, or they can be unstable, and that might cause problems in certain practical aspects, not in every one, because there are non-minimum phase systems that can still be used in practice, or they have a very strange behavior. They evolve, approaching stable equilibrium and then being drifted to an unstable influence by some other close by eigenvalue of that particular part of the state space. And you might even have chaotic responses in those zero dynamics. We will see that it goes both ways. And I can give you a very simple example in which the zero dynamics is not, although being unstable, is not that inconvenient physically speaking. We will see an example of that further ahead. And the simplest example probably is a motor. You know, in a motor, the position of the motor is unstable. If you run it to constant speed, the angular position is growing to infinity. But nobody gets harmed because the motor is running at constant speed. And that's sort of a zero dynamics because you control the motor so as to have constant speed, and the angle kept growing and growing. And nobody loses sleep over the growing angle in the motor that is operating at night in your basement. So that's the interesting thing that can go both ways. On the other hand, if those variables correspond to a current in an electric circuit, that current growing indefinitely is very dangerous. And the thing is, you wouldn't notice it in the variable that you're controlling because that's stable, and the instability comes from the part that you cannot observe and then control. And that's typical in power electronics. So you have to be careful about the zero dynamics. This is something that's very important. We will have a chance to see that in full detail, the next few examples and so on. Thank you, Rafa.
Thank you, Professor.
As always. Any other question?
Yeah, can I ask a question?
Yes, please.
I know the stuff that you're talking about today relatively well, the Lie derivative, the zero dynamics, and the feedback linearization. But I only know those things in continuous time, and I've never realized there exists a discrete version of this. So could you please briefly mention the history of this in this area, the discretization part?
Yeah, it is interesting that this area was sort of neglected for some time in nonlinear case, but there were people that were doing very important research in this area for practical purposes, and I should mention a couple of names that were responsible for bringing up the attention of these systems in the nonlinear arena. One of the first persons that I met who had been doing some work in this area in parallel with the continuous time case was Michel Fliess. And he had a student at the time, Professor Norman Sira. She did a number produced a number of results in this area for nonlinear systems. in her cooperation with another professor from Italy of the name of Salvatore Monaco. So in the 80s, maybe, you will find some papers by Michel Flees and some of his students in a very nice abstract way, and also papers by Norman Sirot and Salvatore Monaco. And then Isidori himself worked out the discrete time case in one of his seminal books. And after that, the names I remember very distinctively are those of Jesse Grisel, that did wonderful work using linear differential algebra for the treatment of these systems. And there were people like Eduardo Aranda in his PhD thesis doing the feedback linearization problem for the multi-input system, which turns out to be very interesting and quite challenging. As far as I know, of course, the work of Ule Kota is remarkable. She has a very nice book on nonlinear systems. Is a very rigorous book that you can also follow in order to obtain a very good grasp of nonlinear discrete time dynamics. The way I'm presenting it is probably different, a little bit different. I'm not claiming that this is a better way, it's just different. And at least for me, it was easier to understand these systems using this sort of parallelism with linear and nonlinear continuous time systems.
Mm-hmm. Mm-hmm. Yeah, that's very helpful. Thanks a lot.
You're welcome. Any other question? Good. I'll call it off at this point, and thank you for your presence. We'll be ready to have another chat next Thursday, and take good care of yourselves and of your dear ones, and see you next Thursday.
Thank you very
thanks
much,
a lot.
Professor.
See you next week.
Thank you for your patience and your attention.
Yeah, really appreciate it.
You're welcome. Bye-bye.